Imagine looking 13.8 billion years into the past and seeing something 46 billion light-years away. The universe isn't just expanding, it's outpacing the speed of light itself. But how do we calculate the size of this impossible cosmic arena? The cosmic microwave background glows at 46.1 billion light-years away, the edge of what we can see. But that distance isn't just a number. It's a whisper from the universe's infancy, stretched by time itself. In 1922, Alexander Friedmann found Einstein's equations refused a static universe. They demanded motion. Spacetime itself must either expand or collapse. Einstein initially resisted. He added a cosmological constant to force stillness. But the math was unyielding. The universe couldn't be a frozen painting. It had to breathe, to pulse, to evolve. Today we know the universe's size isn't fixed. It's a living equation. A balance of time, expansion speed, and the energy in every cubic meter of space. Dark matter, dark energy. Even the void hums with hidden mass. So how do these invisible forces shape the edge of our vision? Friedmann's equations hinted at answers, but they needed Chinese letter. Evidence. By the 1920s, astronomers began mapping galaxy motions. They saw something strange. Galaxies weren't just moving, they were fleeing as if space itself was inflating. But how do we translate that ancient math into precise cosmic measurements? The answer lies in light, in how it stretches as the universe expands. Every photon from the CMB carries a story of 13.8 billion years of cosmic stretching. Yet we see it now as a sphere 46 billion light-years across, a paradox of time and space. And the question remains, what will that edge look like when the universe is twice its age? If this kind of wonder keeps you up at night, you're in the right place. Subscribe so you don't miss what comes next. In 1919, starlight bent around the sun told a new story of gravity. Einstein's theory wasn't just equations, it was a map of spacetime itself. By 1916, Karl Schwarzschild had found a solution to those equations. His math predicted a point where gravity curves space so fiercely not even light escapes. A black hole, born not from fire but from the geometry of emptiness. But the universe itself remained a static stage until 1922. Alexander Friedmann scribbled equations that shook the cosmos. He showed the universe's size isn't fixed, but dances with energy and curvature. A universe filled with matter would slow its expansion. But what if the rules changed mid-dance? By the 1990s, supernovae revealed a shocking truth. The universe isn't slowing. It's accelerating. Empty space itself is a factory, churning out more of what it contains, dark energy. The more space you have, the more dark energy appears, like an infinite echo. But here's where it gets strange. Dark energy doesn't just push galaxies apart. It stretches the very threads of spacetime. Light tries to travel, but space outpaces it. The farthest galaxies aren't moving through space. Space is moving them. Now rewind. When we say the universe was once the size of a soccer ball, how do we measure something vanished? The answer lies in a clock written in the fabric of the cosmos. Friedmann's equations are more than math, they're a cosmic diary. They let us read the age of the universe from its size. At 1 nanosecond old, it was denser than a neutron star. At 3 minutes old, nuclear fusion forged the first elements. But how do we know these scales? The same equations that predict today's 46 billion light-year horizon also trace the past. They tie the universe's growth to the energy in it: matter, radiation, dark energy. Each era has a signature, imprinted on light and structure. The cosmic microwave background whispers of a time when the universe was a molten sea of particles. Its temperature fluctuations are a fossil of quantum ripples stretched across space. But those ripples had to start somewhere. What about the instant before the soccer ball era? When the universe was smaller than an atom. Inflation theory suggests a burst of exponential growth, smoothing wrinkles into flatness. But inflation isn't magic. It's driven by energy, just like today's acceleration. So the same rules apply, backward and forward. From infinitely small to infinitely vast, the universe obeys a single clock. We've mapped its ticking from the Big Bang to the farthest galaxies. And yet, the soccer ball question lingers. How do you measure something that no longer exists? By listening to the echoes it left behind. The observable universe's size is calculated by tracing backward through 13.8 billion years of expansion. We rewind the cosmic clock, watching galaxies retreat as spacetime expands in our imagination. Every measurement, from galaxy distances to CMB patterns, confirms Friedman's equations. The math doesn't just fit, it sings. A symphony of expansion, born in 1915, validated by starlight bent during eclipses. But what if the equations are hiding something, a whisper in the dark we haven't yet deciphered? Philosophical closure comes in a twist. We're not seeing space, we're seeing the evolution of spacetime itself. Each photon we catch is a fossil of geometry, a memory of how the universe stretched and cooled. The soccer ball, the child, the ancient fireball, all are not sizes, but moments frozen in motion. What lies beyond our 46.1 billion light-year horizon? A question older than starlight. The answer may forever remain beyond reach, not because it's unknowable, but because we can't see what we don't yet understand. Our telescopes are time machines, but they can't peer into the dark without a beacon. And it gets stranger. The universe isn't just expanding, it's stretching faster than light in some places. So distant galaxies vanish not by moving away, but by crossing a horizon we can never touch. Like ripples in a pond that outpace the water, their stories end before they reach us. Yet here we are, decoding the echoes, mapping the edge of the knowable with math older than galaxies. What if the true shape of the cosmos isn't in the stars we see, but in the silence between them? Friedman's equations describe a universe that bends, but not all bends are visible to the eye. The final paradox: the farther we look, the younger the universe becomes, and the more it defies our grasp. We measure not with rulers, but with light and time, stitching together a map of what once was. If the universe has no center, then where are we in its infinite expansion? If this journey stirred something in you, leave a like. It helps whispers of the universe reach more curious minds. And hit that notification bell so the next wonder finds you first.